Uniform corrosion, also known as general corrosion, is basically a process where a material corrodes uniformly. For example, etching, when the material forms into contact with acids. The first sign of this type of corrosion is the dulling of the freshly polished surface, like these silver coins and jewelry over here. The mechanical properties are not much affected at this stage, but if corrosion is ignored, then it keeps progressing, and eventually the material no longer serves its purpose. As you can see, this axe head is already quite corroded, but then again it's quite thick, so the mechanical properties have not changed much, and it would still serve its purpose to clean off the zombie's head. The other option is to use protective coatings that prevent the corrosive substances to come into contact with the material. Pitting corrosion is a localized form of corrosion that leads to the formation of small pits or cavities on the surface of a metal. It occurs when a small area of the metal is exposed to a more aggressive environment, while the surrounding area remains relatively protected. This can happen due to various factors, including exposure to corrosive substances, mechanical damage, or the presence of impurities on the surface. In the second stage, a localized corrosion cell forms within the pit. The pit acts as an anode, while the surrounding area acts as a cathode. At the anode, metal atoms lose electrons, leading to the formation of metal ions. At the cathode, reduction reactions occur. Oxygen reduction is typically the dominant cathodic reaction in the presence of dissolved oxygen. In the third stage, the hydroxide and chloride ions react with the metal in the pit, gradually making the anodic region more acidic. Detecting pitting corrosion can be challenging, particularly in its early stages when it may not be readily visible. Here are some methods commonly used to detect and assess pitting corrosion. Visual inspection of the metal surface may reveal signs of pitting corrosion, which include localized pits, depressions, or irregularities. Pitting corrosion often appears as small, circular or oval-shaped craters on the surface. The use magnification tools such as magnifying glasses, microscopes, or borescopes to closely inspect the surface for microscopic pits that may not be visible to the naked eye. High-resolution imaging techniques can help identify and quantify the extent of pitting corrosion. Surface probes and profilometers can be used to measure the surface roughness. Pits tend to result in increased surface roughness compared to the surrounding area, making them detectable through such measurements. Corrosion sensors can be installed onto metal structure to monitor and measure corrosion rates. Changes in the measured values over time can indicate the presence of pitting corrosion. To prevent pitting corrosion, it is important to implement proactive measures to protect metal surfaces. Here are some effective strategies for preventing pitting corrosion. Choose corrosion-resistant materials for applications prone to pitting corrosion. Stainless steel, aluminum alloys, and other non-corrosive metals can offer better resistance to pitting corrosion compared to carbon steel. Apply protective coatings, such as paints, varnishes, or corrosion-resistant coatings, to metal surfaces. These coatings act as a barrier, preventing the exposure of the metal to corrosive substances and reducing the risk of pitting corrosion. Implement cathodic protection methods, such as sacrificial anode systems or impressed current systems, to protect metal structures from corrosion. These techniques involve the introduction of a sacrificial metal or an external electrical current to create a protective electrical potential that prevents pitting corrosion. Design structures and components in a way that minimizes the presence of crevices, gaps, or areas prone to stagnant or trapped corrosive substances. Smooth, well-sealed surfaces reduce the likelihood of crevice corrosion, which can lead to pitting corrosion. Conduct routine inspections and maintenance to identify and address early signs of corrosion, including pitting corrosion. Promptly repair or replace damaged protective coatings, address any surface damage, and take corrective actions to prevent corrosion from progressing. Manage environmental conditions to reduce the risk of pitting corrosion. This includes minimizing exposure to moisture, controlling temperature and humidity levels, and limiting contact with corrosive substances such as salt water, acids, or chemicals. Consider the use of corrosion inhibitors, which are chemical substances that can be applied to metal surfaces to provide temporary protection against corrosion. Inhibitors work by forming a protective film or altering the corrosion potential of the metal, inhibiting pitting corrosion. Ensure appropriate pH levels in environments where metal is present. Avoid acidic or alkaline conditions that can accelerate corrosion, including pitting corrosion. Regularly monitor and adjust pH levels if necessary. By implementing these preventive measures, it is possible to significantly reduce the occurrence and progression of pitting corrosion, prolonging the lifespan of metal structures and components. The mechanism of crevice corrosion is quite complex as it involves multiple stages. In the first stage, a crevice is formed, which can occur, for instance, by inserting a bolt into a plate. This creates a narrow space between the two metal surfaces, where the diffusion of substances becomes hindered, leading to the stagnation of corrosive substances such as seawater. Due to naturally occurring reactions, the oxygen quickly depletes in the gap, and the concentration of metal ions increases. This leads to the formation of a galvanic couple, with the crevice becoming anodic and the surrounding area becoming cathodic. In the second stage, the galvanic couple promotes corrosion in the crevice through the reduction of oxygen at the cathode. Consequently, the positive potential at the anode attracts negative hydroxide and chloride ions into the crevice. Within the crevice, the hydroxide and chloride ions react with the metal, gradually making the anodic region more acidic. The third stage is triggered when the pH within the crevice drops to a critical level, causing the breakdown of the passive layer. At this point, corrosion progresses rapidly until the structure eventually falls apart. Detecting crevice corrosion can be challenging as it often occurs in concealed or hard-to-reach areas. However, there are several methods that can help identify its presence. Detecting crevice corrosion through visual inspection involves a thorough examination of metal surfaces, with a focus on crevices, joints, and areas where metals meet. Look for localized damage such as pitting or roughness, along with discoloration or staining around crevices. Pay attention to changes in texture or the presence of deposits or debris. Monitor for signs of leakage or staining. Preventing crevice corrosion involves implementing effective strategies to mitigate the factors that contribute to its occurrence. Here are some key methods to consider. Proper design and construction. Start by designing structures or components with minimal crevices or incorporating smooth transitions between metal surfaces. Avoid creating crevices or gaps where moisture can accumulate. Adequate sealing or gasket materials should be used in joints or connections to prevent the ingress of corrosive substances. Protective coatings. Apply suitable protective coatings to metal surfaces to create a barrier against moisture and corrosive agents. Coatings such as paints, epoxy coatings, or corrosion-resistant films can help seal crevices and provide a protective layer, reducing the likelihood of crevice corrosion. Regular monitoring, maintenance, and periodic assessments of the corrosion prevention measures will ensure their ongoing effectiveness in preventing crevice corrosion. Intergranular corrosion. There are different grain boundaries in metals. So, the corrosion is observed where the grain boundaries of crystallized of the material are more susceptible to the corrosion than their insides. So here, that corrosion takes place externally. And that is in the presence of tensile stress. Here, cracking may occur along the grain boundaries. That's why, in between the grain boundaries, the corrosion that can be observed into the metals. So that small grain boundaries acts as anode, and rest of the part of the metal acts as a cathode. Here, it is visually recognizable, as in the case of weld decay. So here, dwelling of the metals or joining of the metals are there. The corrosion is observed at that particular part. And galvanic corrosion is an accelerated form of corrosion, as it is an electrochemical process that occurs when two metals with different electrochemical activity are in an electrical contact with each other. In this process, the more passive metal drives the corrosion of the active metal, and at the same time, the passive metal remains unharmed. The process would keep going on until the active metal is completely gone or the electrical connection between the two broken. Another example would be an aluminum frame that is connected with steel screws. Aluminum is much more active than steel, and thus the steel screws drive the corrosion of the aluminum frame. So if this construction would be closer to the sea, where we have lots of chloride in the air, then pretty soon the steel screws would start falling out, as the surrounding aluminum has corroded away.